Hello, chemistry. Here is our lesson on sig figs, uncertainty, and moles. We had a nice introduction to this at the end of this past week in class. We're going to go ahead and review, clarify, embed in your brains a little bit better this idea of sig figs and uncertainty, and then we're going to introduce the mole. So remember that uncertainty is just this idea that some of our measurements maybe have some wiggle room embedded in them, and we just need to make sure that when we're recording our measurements, we are fairly cautious of how we're sharing that wiggle room. So we can note our uncertainty with this plus or minus give or take chunk of our measurement. So we know for sure our certain digits. The last one is always going to be our uncertain digit or our estimated digit. And then we'll have that plus or minus whatever the range of our estimate might be. For now, just to keep this idea fairly simple to start, we are going to say that our estimated range, our give or take, is going to be one of the last place value, one of the uncertain digits place value. So if we end in a tenth, it'll be plus or minus a tenth. If we end it in a thousandth, we do plus or minus a thousandth. Later on, we'll talk about some more complexities with how we calculate different situations. But again, for now, we'll stick with one of that last place value. All of this is related to the idea of accuracy and precision in science. So accuracy is getting the accepted quantity, how much something really, really is. And then precision is being able to repeat a quantity multiple times. So worst case scenario in the lab is that there's no accuracy and no precision. Your measurements are just crazy off the mark. This one, having low accuracy but high precision, is also really bad because you're getting the same number over and over and over again. And so you're fairly confident that it must be good, but it's like way off every time. So this might happen if your scale was broken and you're measuring a rock, you put the rock on the scale, you take it off, you put the rock back on the scale, and every single time the scale is maybe adding a gram to your rock. So this is bad because we have false confidence. This one's better. We have better accuracy, but now our precision is off. And this is usually due to random errors, we humans not using our equipment appropriately, where we're fairly close to what we need to get, but that we're not necessarily getting the same value over and over. Best case scenario, of course, is to get the right number repeatedly. So quick review of reading volume in our graduated cylinders. We are going to look at, let's go blue today. We're going to look at what we know for sure. We know 60, 61, 62, 63. So here are our certain digits. This one I'm going to guess because there isn't a tick mark. So I'm going to go 0.4, which of course isn't necessarily right. And so I'm going to show that I'm off by a tenth because my last place value was a tenth. So there's my uncertainty. So all of our measurements, our certain and our uncertain digits in a measurement are considered significant. And it's really important for us to be able to recognize what numbers are significant in pieces of data and which are not. And so we have some rules. And we talked about all of these rules in class last week, with the exception of number 5. And we're not going to worry about number 5 yet because we're not talking about common logarithms until the spring semester when we learn about pH. So don't even worry about that for now. Important rules for us to know: non-zero digits, of course, those are the ones 1, 2, 3, 4, 5, 6, 7, 8, 9. These are always going to be significant. Zeros between non-zero digits are always significant. So if you had like 9,001, since these guys are between non-zero digits, these guys are significant. Leading zeros, however, are not ever significant. So that's going to be like a bunch of zeros in front of a decimal place. None of those are significant. They're just placeholders. Zeros to the right of non-zero digits are significant only if there's a decimal point. So if you had 200, only this guy's significant. These ones are not significant unless we throw in a decimal point. Now all the zeros are significant. And then if we have things written in scientific notation, everything in the coefficient is significant. So 2.013 times 10 to the 12th, everything here, all four of those digits are significant. 5 times 10 to the negative third, only that 5, that one digit is going to be significant. So let's practice some more counting sig figs. Here we have 10 practice problems. Pause the video, count these sig figs, and then come back and check your answers. And I'm assuming you are ready for some answers. So this one has 2 sig figs. We have a non-zero here at the end, so all 5 of those end up being significant. Remember that zeros between non-zeros are significant. These leading zeros are not significant, so these guys don't count. But the 402, all 3 of those do count because this zero is between 2 non-zeros. Again, leading zeros are not going to count. These guys, all 4 of them do count because this zero comes to the right of a non-zero following a decimal. Here again, we have a decimal, so all 3 of those are significant, no decimal. So the zeros are not significant, only the 5 is. Same idea, only that 1 is significant, but this one, notice, has a decimal, so all 3 of those are significant. Everything in the coefficient, all 4 of those digits are significant. Only one digit in the coefficient is going to be 1 sig fig. So when we are calculating with our sig figs, we need to follow a couple different rules. So the first one for multiplying and dividing, again, we talked about this in class late last week. We're going to count the number of sig figs in each piece of data. We're going to round our final answer to the smallest number of the sig figs in the data. So for example, if I am looking at this plot of whatever, and I want to find the area, I'm going to multiply 2 meters by 3.782 meters. That gives me 7.564 meters squared, according to my handy-dandy calculator. But this is rounded to 2, which means really it could be anywhere between maybe 1.5 meters to 2.4 meters. Somewhere in there is what this width is. So if I'm rounding so much the width, I can't really truly say that I know the area down to the thousandths of a square meter. What I can say, though, is 1 sig fig. So I've got 1 here, I've got 4 here. 1 is the smaller number of sig figs. So my final answer is going to be rounded to 1 sig fig. So this 5 is going to turn that 7 into an 8. And this is the better answer for area. It's about 8 square meters. This is more truthful. This, we're making up stuff that we don't really know for sure. So let's go ahead and practice some of our calculations. So multiplying and dividing, remember you're going to count the number of sig figs. Your final answer will have the same number of sig figs as the piece of data with the smallest number of sig figs. Pause the video, come back and check your answers. All right, let's do some answers. So 3.1 times 405 is going to give us 12.555 centimeters squared. We have 2 sig figs. We have 3 sig figs. This means that we can keep only 2. So we're going to keep 1, 2. That 5 is going to turn that 2 into a 3. And so our final answer should be 13 square centimeters. 45.0 times 16 gives us 720. Our grams cancel out. We're left with moles. We have 3 sig figs. We have 2 sig figs. 2 is less than 3, so our final answer needs 2 sig figs. It already has only 2, so this is our final answer. 720 moles. Do not put a decimal there, though. 88.5 meters divided by 50 meters per hour is going to give us 1.77 hours. Our meters cancel out. We have 3 sig figs. Here we only have 1. There's no decimal, so that 0 doesn't count, which means that our final answer can have only 1 sig fig. that 7 is going to round that 1 up to a 2, and this is our final answer, about 2 hours. And last but not least, 3 times 10 to the 8th meters per second. There's no function here, so we're going to assume multiply. Times 6.8 times 10 to the 3rd seconds. Our seconds cancel out. We end up with 2.04 times 10 to the 12th meters. We have 3 sig figs. We have 2 sig figs. Our final answer can keep only 2. We're going to keep 1, 2. That 4 leaves that 0 at a 0. And so our final answer is 2.0 times 10 to the 12th meters. So this again is our rule for multiplying and dividing. We have a different set of rules for adding and subtracting. Here we're going to look at the place value of the last significant figure in each piece of data, and we're going to round our final answer to the largest of those place values. So again, go ahead and practice. Pause the video, get these done, come back and check your answers. And it's answer time. So when we add these up, 5.935 meters and 6.92 meters, we're going to get 12.855 meters. We're going to look at the last place value. This 5 is in the thousandths place. This 2 is in the hundredths place. Hundredth is bigger, and so we're going to keep the hundredths place in our final answer. The 5 turns that 5 into a 6, so our final answer is 12.86 meters. Next one, 24.1 grams minus 12.599 grams gives us an answer of 11.501 grams. We have a tenth. We have a thousandth. Tenth is bigger, so our final answer needs to be rounded to the tenths place. The 0 leaves that 5 a 5, and so our final answer is 11.5 grams. 5.3 milliliters and 15 milliliters added to 200 milliliters is going to give us 220.3 milliliters. Are you ready for this craziness? It's a tenth. It's a ones place. Biggest place value of a sig fig here is a 2 in the hundreds place. This is our only sig fig, and so it's going to be the last place value, and it's the biggest of these 3 pieces of data, which means that we need to round our final answer to, oh my goodness, the hundreds place. This 2 leaves that 2 a 2, and so we get 200 milliliters. But wait, how can we possibly have 200 milliliters, add 15 and 5.3 more milliliters and still have only 200 milliliters? Remember that this is rounded. This is telling us anywhere between really 150 and 249-ish. So if we had only 160 and we added, we are still going to have only about 200. If I had 220 and I added, I'm still really going to only have about 200. Since I don't know any more than somewhere around 200, I really can only say I still have somewhere around 200. And one more example. This one, not quite so mind-blowing. So 65.998 moles minus 42.0006 moles, and that gives us a difference of 23.9974 moles. We have a thousandth place and a 10,000ths place, so we're going to keep a thousandths place in our final answer. That 4 turns that 7 into leaves it at a 7. So our final answer is going to be 23.997 moles. Hopefully this is all making sense. If not, come and see me in tutorials. I will be there before school and after school Monday. So let's look at these 2 numbers and count the sig figs. So this first one is ginormous. So 602 sextillion, 241 quintillion, 108 quadrillion, 979 trillion, 663 billion, 699 million, 470,280 is what that number reads. How many sig figs? Well, all of them except this 0, because there's not a decimal. So that means all of these guys, 3, 6, 9, 12, 15, 18, 21, 22, 23. 23 crazy sig figs in that number. This one is actually also 602 sextillion, but we just like rounded away all those other guys. So now we only have 3 sig figs. So both of these numbers represent what we call Avogadro's number. Avogadro's number. When we use Avogadro's number in chemistry, which we will do a lot, we're going to use this version because 3 sig figs and scientific notation is way easier to work with than all of that big hot mess, which I don't think we even have space on the screens of our calculators to type in. So be joyful that this is Avogadro's number, the version of Avogadro's number that we're going to use in class. Here is Mr. Avogadro himself, Amadeo, perhaps one of the most handsome men to ever grace a science laboratory. And that was supposed to be a joke. Hopefully you smiled or even giggled. But this is Avogadro. Avogadro did not actually figure out Avogadro's number. We just named it after him because Avogadro is known as the father of gas chemistry. He did lots of cool things about gas molecules. His number, Avogadro's number, the mole number, is simply a way for us to count things, but it's a way for us to count piles of lots and lots and lots and lots of things. So we have some other counting vocabulary we're going to review just so that this makes a little bit more sense. So a pair is a quantity that we use to count things. How many shoes are in a pair of shoes? Well, there are 2. There are also 2 elephants in a pair of elephants, 2 people in a pair of people, 2 chairs in a pair of chairs. A pair is 2. Same thing with a dozen, but this one's a little bit of a bigger pile. So now I have 12 things in a dozen. A dozen eggs is 12 eggs. A dozen cupcakes is 12 cupcakes. So 12 is a dozen. Score is a little bit less common of a word. This is actually equal to 20. So if you remember, we chatted a little bit maybe a week ago about Lincoln's speech for score and 7 years ago. So he was talking about 4 times 20 and 7 is going to be 87. So 4 score and 7 is actually 87 years because there's 20 in a score. So if I have a score of elephants, I have 20 elephants. I don't know why I keep talking about elephants. If I have a score of books, I have 20 books. So it's just a pile of things, and there are 20 things in that pile. A gross is a dozen dozens. So we have a dozen dozens or 144 things. So if I have a gross of desks, I have 144 desks. If I have a gross of stickers, I have 144 stickers. If I have a gross of bouncy balls, I have 144 bouncy balls. A million, this one's kind of obvious. There's 1 million things in a million. So if I have a million cats, I have this many cats. If I have a million people, I have 1,000,000 people. How many things do I have? If I have a mole of them, well, I have 602 sextillion. If I have a mole of books, I have 602 sextillion books. If I have a mole of Band-Aids, I have 602 sextillion Band-Aids. Usually we don't count big things with the mole because you can imagine how many Band-Aids 602 sextillion Band-Aids would be. That would be, I don't know, a lot of Band-Aids. We usually use the mole to count really, really, really little things. So if we have a big pile of them, it's not like taking over the whole planet. So the mole we use more often to count atoms and molecules, which are really, really, really tiny. So if we have 602 sextillion carbon atoms, it's actually not that ginormous a pile. And what's amazing about the mole and our periodic table is that our mass numbers can actually do double duty. So hopefully you remember from middle school, the mass number on the periodic table. This is our atomic number. We'll talk about that later. Right now, we're going to focus on this mass number right under the chemical symbol on this version of the periodic table. Well, this piece of this version of the periodic table. So this mass number tells me that the mass of one atom of carbon is going to be 12.011 AMUs. 12.011 AMUs for 1 atom of carbon. But if I have a mole of carbon, if I have 602 sextillion atoms of carbon, and I put 602 sextillion atoms of carbon on a scale, the mass is going to be 12.011 grams. So it's amazing. Number stays the same. We're just changing our label. We go from AMUs to grams. We're going to talk about this a bunch, and we'll talk about it some more, and then we'll talk about it in October, and we'll talk about it in January. So if you're like, I have no idea what she's talking about right now, that's okay. We'll talk about it again, but stick with me as best you can. So if we're talking about carbon, 1 atom is 12.011 AMUs, atomic mass units. What if I'm looking at oxygen? Well, that's going to be 15.999 according to my handy-dandy periodic table, but an oxygen molecule is actually O2. So I'm going to multiply that by 2 because I've actually got 2 oxygen atoms in there. That gives me 31.998, and I'm talking about 1 molecule, 2 atoms. My label's going to be AMUs. But what if I have 602 sextillion molecules of oxygen gas? What if I have a mole of oxygen gas? Well, now all I have to do is change my label to grams. Same mass number, just a different label. So 1 molecule is in AMUs, 1 mole is going to be in grams. And then I can start scaling this up. So what if I had 5 moles of oxygen gas? I'm just going to take that, multiply it by 5, and I get 159.99 grams. So this is the mass of 5 moles of oxygen. Except that's really, really bad scientific or significant figures. So we're going to come back to our idea of sig figs, and we're going to practice this with the mole. So we said that 5 moles of oxygen gas had a mass of 159.99 grams because 5 times 31.998 was equal to that 159.99 grams. So if we have only 1 sig fig in our 5, then I can only keep 1 sig fig in my final answer. So my 159.99, I get to keep only 1. That 5 is going to pop that 1 up to a 2, and I've got about 200 grams of oxygen. If I have 5.0 moles, so now I'm getting a little bit more specific, I get to keep 2 sig figs. And so my 159.99, I get to keep 1, 2. That 9 is going to pop that 5 up to a 6. I have 160 grams of oxygen. Well, what if I have 3 sig figs? I don't want to notice 5.0, but I want to know 5.00 moles of oxygen gas. Well, now I get to keep 1, 2, 3. That 9 pops that 9 up to a 0, which pops that 5 up to a 6. Almost the same thing, except I need 3 sig figs, and so I have a decimal point at the end. And this one, I'm hoping you can guess where we're going. So now I'm keeping 1, 2, 3, 4. That 9 pops that 9 up to a 0, popping everything else up, and so I get 160.0. And I know that these guys look almost the same, but each number is giving us a very different range of possibilities in our estimate. This one is saying it could be really anywhere between 150 and 249-ish grams of oxygen. That's a really big range. I rounded it to 200. Here, I'm saying it could kind of be anywhere between maybe 155 and 164-ish. It's a much smaller range that I rounded to 160. This decimal tells me that I am rounding from like 159.5 to maybe 160.4. My range is getting much, much smaller. And here we get smaller again. So now this is saying somewhere between 159.95 and 160.05. It's a tiny little range of deviation in my measurement. So the more sig figs we have, the better we can trust that measurement, the less deviation we have. And this is the end of sig figs and our introduction to the mole. If you want to know more about the mole, you don't have to yet, so don't have a panic attack, but if you want to know more about the mole, into your search bar on Google or Bing or Yahoo or whatever it is that you use. Just type in TED Ed How Big is Mole, and you'll have a lovely little video. I don't know, I think it's about 5 minutes long, but I'm rounding there, my friends, with a much more fun introduction to the mole than what I did. So that is it for now. Don't forget that there is a quiz coming up. Make sure that you practice your metric system. Make sure you know about sig figs. Come and see me in tutorials if you have questions.